Have you ever wondered how skyscraper buildings and other massive structures can withstand wind and other external factors? If so, let us tell you why.
Hi.
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 Hi. Hi.
Hi.
I am Reymarie Mikaela B. Luyao.
I am Julia H. Hualde.
I'm Johnsen Ricalie M. Fuscablo.
I am Miguel Andrei B. Duterte.
I am Mae Jamio.
I am Jazmin Chua.
I am Meriel, Kirsten, and Bartolome.
I am Trisha Izze Casangyao.
And we are all aspiring engineers.
In this video, we will tackle structural engineering. Structural engineering is a subfield of civil engineering concerned with the design of human-made or artificial structures, often described as designing the bones and muscles of structures. These engineers must comprehend the rigidity, stability, and strength of building and non-building structures. In addition, structural engineering is a fascinating field that combines mathematics and physics to calculate the load subjected to a structure. Additionally, structural engineers can determine the materials and dimensions needed to ensure its safety and durability by understanding the forces acting on a structure. They consider factors such as wind, earthquakes, and even human occupancy to design structures that can withstand various conditions. This intricate process involves analyzing the behavior of materials under different loads and applying principles of mechanics to create sound and reliable structures. But I am wondering, how was this found and developed? Can someone tell me how?
I can tell you why, Reymarie. Let's turn back time and look back at the history of structural engineering. Structural engineering started from Imhotep, the first architect in history who constructed the step pyramid for Pharaoh Djoser around 2700 BC, marking the beginning of structural engineering. Ancient civilizations developed pyramids more frequently than other large buildings because they are a naturally stable structural type that can be scaled literally limitless. The Great Pyramid of Giza, constructed in 2560 BC, was the largest artificial structure for millennia before towers and skyscrapers began to appear in the 19th century. Around the 3rd century BC, the work of Archimedes was published. His estimations of the surface areas and gravitational centers of numerous geometric forms, such as triangles. Most mathematics and structural principles used in modern structural engineering are based on paraboloids and hemispheres. In the 1st century BC, Vitruvius documented the techniques, supplies, and tools the ancient Romans employed to construct constructions like aqueducts, thermae, columns, lighthouses, defensive walls, and harbors in his De Architectura. Additionally, Galileo Galilei described the fields of material strength and object motion in dialogues related to two new sciences, which he published in 1638. The structural analysis was launched with the publication of this book. Robert Hooke's first proclamation of Hooke's Law, published in 1676, offered a rational justification for the elastic properties of materials and their behavior under pressure. Furthermore, Sir Isaac Newton's laws of motion were included in Philosophiae Naturalis Principia Mathematica, published in 1687, and they help people understand the basic principles regulating constructed objects.
Awesome! But who are the people involved in structural engineering? Or what should we call them?
They are known as structural engineers, Migs. The primary function of structural engineers is to create safe buildings and structures that can survive the elements they will be subjected to and enhance the structural integrity of existing structures. The position is relatively similar to that of a civil engineer. Engineers specializing in structural design ensure buildings can resist the strain and pressure from use in the environment. They determine any project's stability, strength, and stiffness, whether a new construction, conversion, or refurbishment, and ensure the appropriate materials are employed. As a structural engineer, you might work on residential projects, retail establishments, commercial buildings, bridges, offshore oil rigs, theaters, medical facilities, museums, and space satellites. Moreover, the structural engineer's responsibility is essential in the building process. In addition to their many other duties, structural engineers are responsible for guaranteeing the project they are working on is safe and durable. Unlike architects, who must focus on the building's appearance, shape, size, and use, structural engineers must solve technical problems and help the architect achieve their vision for the project. Structural engineers must have a firm grasp of physics, three-dimensional concept skills, and creative problem solving. Outside of an ability to apply principles of mechanics, mathematics, and physics to construct safe, sustainable buildings, the roles and responsibilities of structural engineers include design, investigation, communication, and management.
Under design, many structural engineers deal primarily in designing structures, calculating the loads and stresses the construction must withstand safely. Structural engineers should be able to factor in the different qualities and strengths delivered by a range of building materials and understand how to incorporate support beams, columns, and foundations. Under investigation, before work can begin, structural engineers are involved in investigating and surveying build sites to determine the Earth's suitability for the upcoming project's requirements. Under communication, structural engineers will be required to coordinate and consult with other members of their projects, including engineers, environmental scientists, architects, and landscape architects. They may also be required to assist government bodies in their inspection relating to the project. Finally, under management, structural engineers are often responsible for organizing and delivering materials and equipment for the construction project's needs. The supervision and the management of on-site labor may also be a necessity.
Wow, that's quite a lot of responsibilities. Are there rules and regulations that structural engineers must follow? Because this field deals with people's safety.
There is, Meriel. Structural engineers have a code of ethics. This code of ethics applies to the responsible individuals who offers professional services in analyzing, assessing, designing, constructing, or repairing building, bridges, and other structures like structural engineers. Two sections of the Code of Ethics are Fundamental Principle and Tenets. Fundamental Principles: to uphold and advance the integrity, honor, and dignity of the structural engineering profession by using their knowledge and skill for the enhancement of human welfare. Being honest and impartial in serving with the fidelity to public, their employers, and clients, and striving to increase the competence of practitioners and the prestige of the structural engineering profession. The second section is Fundamental Tenets. Structural engineers use their knowledge and skills to perform their professional duties to make public safety, health, and welfare decisions. Perform services only in areas of their demonstrated competence. Issue public statements objectively and honestly. Act for each employer or client as faithful agents or trustees and avoid conflict of interest. Build their professional reputation on merit and compete fairly with others. Act in such a manner as to uphold and enhance the honor, integrity, and dignity of the structural engineering profession without tolerance for corruption. Continue their professional development throughout their careers and provide opportunities for the professional development of others. Engineers are expected to exhibit the highest standard of honesty and integrity as member of this profession. Engineering has a direct and vital impact on the quality of life for all people. Accordingly, the services engineers provide require honesty, impartiality, fairness, and equity, and must be dedicated to protecting public health, safety, and welfare. Engineers must perform under a standard of professional behavior that requires adherence to the highest principle of ethical conduct.
Oh, that's a lot of rules and ethics to follow. Indeed, structural engineers have a challenging and significant role and purpose in our society. But I am wondering, what are the essentials of contributions of structural engineering in our community?
I can tell you, Meriel, structural engineers, or SEs, help governments, institutions, developers, and architects analyze the natural and artificial factors that impact a structure's integrity and longevity. SEs design the elements that hold up buildings, tunnels, bridges, and more. They focus on maximizing safety and stability within the constraints of the construction project and the physical environment. A licensed structural engineer is required for every construction project. As a result, they play a role in various projects that touch on every aspect of our lives. This can come in different ways, such as withstanding the force of nature. Every building, from your local supermarket to the towering skyscrapers in your city, requires a structural engineer's input in the design and analysis stage. To do this, they use their expertise to overcome environmental obstacles. Natural calamities can significantly affect the environment, including natural phenomena like earthquakes, snowstorms, and high winds. Earthquakes are the most common natural phenomenon that can happen in the Philippines. Earthquakes can cause visible, extreme damage when the magnitude is high enough. But even minor seismic shifts can cause damage to architectural finishes over time. Thus, structural engineers design to minimize seismic risk and maximize seismic performance. In other words, they seek to create structures that perform well during and after an earthquake over long periods. Structural engineers anticipate the various ways a building can fall due to an earthquake and implement structures with the necessary strength, stiffness, and ductility to withstand the most likely sources of failure. Earthquake patterns change yearly due to natural developments and human activities, which is why structural engineers are needed to ensure buildings can withstand earthquakes of any magnitude now more than ever. Snowstorms, though not common in the Philippines, have a massive impact on other countries. Structural engineers must consider the amount of snowfall and ice a building will encounter and choose materials and construction techniques to create the most supportive structure. To prevent this, they calculate the snow load per square foot that a building will experience and design with this in mind. And each state sets its minimum standards. Next is high winds. They can be destructive as they generate pressure against structures frequently. A powerful gust can even sway skyscrapers. Hurricanes are an example of extreme high winds. Structural engineers must also reinforce buildings against regular thunderstorms and windy days, as these pose a constant threat to the long-term stability of a structure. The intensity of this pressure is known as the wind load. Structural engineers use this load to design safer, more wind-resistant buildings. The speed of potential winds, the height of the building, proximity to water, and proximity to other structures are critical factors in the analysis. They also consult historical records and building codes to determine the support and strengthening required for a project. Using predictive models, structural engineers can anticipate potential challenges and prevent life-threatening situations posed by high winds. Another significant contribution of structural engineers in the transportation sector, like safe bridges and tunnels. Structural engineers are pivotal in ensuring bridges and tunnels can support forces and provide safe transportation. Two significant benefits these well-engineered structures provide are freedom and flexibility. Efficient and safe transportation routes allow individuals to choose where they live, work, and socialize based on various preferences. People can access resources from a distance and don't need to live within a certain mile radius to benefit from modernization. Travel between and within suburbs, cities, and states is possible and effortless. Large trucks can carry resources long distance without damage due to heavy loads. Ships can easily pass through bridges designed to rise and lower, meaning trade routes don't interfere with day-to-day life. These conveniences are enjoyed daily but go unnoticed precisely because the systems are effectively engineered. Another contribution is in the environmental aspect, specifically soil, water, and sustainability. Before construction begins, a structural engineer analyzes the area to ensure it suits the proposed building, tunnel, or other structure. They'll ensure the soil conditions are supportive and manage any usual soil conditions. As a result, anything built on top of the land will remain level, stable, and have greater longevity. Structural engineers work to ensure that structures don't adversely impact groundwater sources. They also work with an eye towards sustainability in the future by analyzing materials efficiency, ability to be recycled, and environmental impact. They continuously strive for innovative and effective ways to create lasting structures while supporting environmental practices.
In the anti-terrorism defenses, structural engineering has a significant impact. Structural engineers are trained to ensure that buildings stand up to blast forces. Any structure considered a potential target for terrorism, government facilities, monuments, military installations, must be resistant to progressive collapse and reinforced against blasts. SEs can also identify weak points in existing buildings and help strengthen the structures that present the most significant risk. When terrorists plan an attack, they assess the potential damage they can cause. Buildings without structural weak points require more effort and resources to destroy, so these targets are less attractive. In addition, structural engineering has a humanitarian contribution. In times of disaster or infrastructure collapse, structural engineers are at the forefront of analyzing the stability of the impact buildings and structures. SEs often work with humanitarian organizations and the government to relieve developing or recently devastated areas. Their input helps coordinators make effective decisions to keep populations safe. Suppose a natural disaster struck an area. In that case, an SE can also help with rebuilding, ensuring all renovations and new constructions will not just replace the destroyed building, but improve its structural elements to withstand similar future situations. Furthermore, in the demolition aspect, structural engineers make sure that buildings are demolished safely and efficiently. Even though demolition is the reverse of construction, many of the same principles and safety concerns apply. The order in which a building is dismantled matters. It poses a safety risk if the wrong structural elements are removed or weakened at the wrong time. Structural engineers help to maintain an optimal demolition process by coordinating the process and the techniques used. Lastly, is its contribution to space exploration. Structural engineers aren't just necessary here on Earth. Their work helps us explore the universe. At NASA, engineers are responsible for ensuring the safety of shuttles, space stations, and astronaut crews. SEs are part of the beginning process, identifying risk and making suggestions to protect structures and the people in them. Their skills help NASA navigate outer space hazards. As a team of engineers who genuinely appreciate a job well done, we can't help but see beauty and ingenuity in the feats of engineering all around us. The next time you're out and about, consider a structural engineer's role in creating the simple and amazing things you see around your society.
Amazing! I was shocked at significant structural engineering's contributions are.
Indeed, Meriel. I was also astounded by how diverse and significant the contributions of structural engineering and structural engineers are. However, I am wondering how these structures are built. Like, what are the elements and materials needed to create these impressive structures?
Let me tell you, Izze, Structural engineers use any of these components to create a structure, which can then be categorized based on shape.
Additionally, it may be either one or two-dimensional. The first element is columns. A column is a component used in structural engineering that solely carries out axial force or compression while supporting the weight of the structure above it on the structure beneath it. The axial and buckling capacities of the element below should be considered while designing a column. The second element is beams. A beam is a structural element supporting loads perpendicular to its longitudinal axis. Beams are typically horizontal and used to support the weights of roofs, floors underneath, and ceilings. There are types of beams which are used for different purposes. The third element is trusses. It is a system frequently utilized to sustain structures over a large area. It is composed of nodes, connection joints, and members. While being joined together using joints, these members act in compression or tension. Each part of a truss is structurally constructed to be effective and systematized to maintain the structure's long-term stability and durability. The fourth element is plates. Plates are structural parts with a thinner thickness than other dimensions and are three-dimensional solids. In essence, thin plates are flat structural components joined by two parallel planes known as faces, whereas a cylindrical surface is known as a boundary or edge. On the other hand, the thickness of the plate is the distance between the plane faces. The fifth element is shells. Shell elements are typically used in modeling structures whose thickness is significantly less than that of the other dimensions, and these structures are generally lightweight in construction. They are typically curved and put together to form larger structures. Boat hulls, huge structure roofs, and airplane fuselage all contain shell-like components. The sixth element is arches. An arc is a curving structure that transmits compression forces solely in one direction. These are utilized frequently for aesthetic and design reasons. Finally, the seventh element is the catenaries. A catenary is an object supported at both ends and has a curve created by its weight. Think of the letter U as having its two ends above and its central half sunk inside a curve.
Wow! Now that I know some elements and materials used to create structures, I want to see some of the key milestones of structural engineering.
The history of structural engineering is a vast and fascinating journey through time. Here are some key milestones. Number 1. Ancient civilizations. Ancient Egyptians built impressive structures like the pyramids using simple structural techniques. Ancient Greeks developed principles of geometry and load-bearing columns, influencing later architectural and engineering designs. Number 2. Roman Empire. Romans advanced concrete technology, enabling them to construct massive structures like the Colosseum and aqueducts. Arc and vault systems were widely used, showcasing innovative engineering. Number 3. Middle Ages. Gothic architecture emerged with pointed arches, ribbed vaults, and flying buttresses, allowing for grand cathedrals and churches. The development of timber-framed structures in Europe was significant. Number 4. Renaissance period. Leonardo da Vinci and others explored structural concepts, but formal engineering as a discipline had yet to develop. Number 5. Industrial Revolution. The rise of iron and steel industries led to development of iron bridges and buildings. Engineers like Gustave Eiffel and Robert Stephenson made significant contributions to structural engineering. Number 6. 20th century. Reinforced concrete became prominent, offering versatility and strength. Innovations in materials, computer-aided design or CAD, and seismic engineering advanced the field. Number 7. Modern era or the present.
Skyscrapers, long-span bridges, and innovative architectural designs became possible with materials and engineering software advances. Sustainability and earthquake-resistant design principles gained importance.
Awesome! Indeed, structural engineering's history has come a long way.
Indeed, Eyes, through this sharing, I understood and learned more about how critical and crucial the role of structural engineering and structural engineers is in our society. Without them, we would not be able to have a community where we feel safe and secure. Also, as an inspiring engineer, my passion and drive to succeed in this field to help our community has intensified. And I hope you all feel the same too. Till our next sharing, my dear friends. Padayon, future engineers.